So looking at question number 14, it gives us the equation of the horizontal sway as h equals 40 sine of 0.526t, and the h represents the horizontal distance in centimeters that an office tower sways from the wind. And so for part A, it says graph the function using graphing technology. So plugging into our Desmos, we can get a picture that looks something like this. Okay, so it starts at 0, goes up to a maximum of 40 centimeters to the right, and then down 40 centimeters to the left. And this keeps on going back and forth. So part B says guest arrives at the top floor at t equals 0, and it asks how far has the guest swayed from vertical at 2.034 seconds. For part B, we're just going to plug in 2.034 seconds into that equation. And when we do that, we get multiplying 0.526 by 2.034. And putting that to sine, we end up with 35.08. So I'm just going to round that to 35.1. And this is centimeters. So if we take a look at 2 seconds, we're going to be somewhere around here, and that works out to be 35.1, which is about correct on our graph here. Okay, so that's going to be 35.1, and that's going to be happening at 2.034 seconds. For part C, it says if a guest arrives on the top floor at t equals 0, how many seconds will it have a time elapsed before the guest has swayed 20 centimeters. So if we take a look at the h value, it's going to be 20. So I put 20 on our graph. And the time that we're looking for is t1. So where it's going to hit the 20 centimeter mark the first time. It will hit 20 centimeters on the way back. But we're looking for the first time. So we're looking for t1 here. So to do this, we've been given the h value. So we've been given h equals 20. So I'm just going to put this into an equation. So I have 20 is our h value, and it's equal to 40 sine of 0.526 t, and we're going to solve this. So we're going to first of all divide both sides by 40. So I get 1/2 equals sine of 0.526 t, and then undoing this, the arc sine of 1/2, it happens to be an exact value, so that works out to be in this case it's going to be arc sine of that's going to be 30 degrees, or pi over 6, and that's equal to 0.526 t. And then solving for t, that's theta 1. That's going to be equal to, so I'm going to write that as theta 1. That theta 1 works out to be, well, that's approximately equal to 1 second. Okay, so pi over 6 is approximately 0.526. Okay, so that t1 that we have here, that's going to be 1 second. So it looks like, in fact, you can kind of see that that is fairly accurate. Now, this issue of theta 2 we should address, because once we solve this equation here for theta 1, there is this issue of theta 2. So we can write it this way. So I have 0.526 t as theta 2 is going to be equal to, for sine, it's going to be pi minus theta 1. And so solving for this, we end up with 0.526 t is equal to 5 pi over 6. So our other time that we get, we're going to end up dividing this, and we're going to get about 5 seconds. Okay, and we can see that t2 here is at 5 seconds. And it involves solving the equation, undoing that equation, solving for the angle, and then solving for t. When we solve for the angle, we also have to consider theta 2. So this is our theta 2, that represents our theta 1. So we have to be careful that we always solve. We have two angles that we have to consider anytime we solve this. So in this case, our first angle was allowed us to calculate the time that we were looking for. In this case, it was 1 second.